So we are very happy to have Isabelle Shankar from UC Berkeley, and she's going to talk about Symmetry Adapted Gram Spectrahedron. Go ahead.
Yeah, so let me go into full screen and just again, thank you for the organizers for inviting me. Really excited to be here and really excited to talk about Symmetry Adapted Gram Spectrahedron. Um, so to those of you who were in the pre-seminar, there will be a little bit of repeat. I'll be talking about symmetric polynomials and sums of squares. But to start, I should say that this is joint work with Alexander Heaton and Serkan Hosten. Yeah, so I'll talk a bit about symmetric polynomials and writing them as sums of squares. So there'll be some repeated slides, though I will go a little bit faster. I will then talk about properties of what I call the symmetry adapted PSD cone. And then I'll go into particular examples of symmetry adapted gram spectrahedra that we kind of go over in our paper. And I will end with an application of all this machinery to symmetric polynomial inequalities. So sums of squares, we'll start there. I'm going to start with a polynomial p, and it's homogeneous of degree 2d. Then the key fact that we use is that a polynomial p is a sum of squares, SOS, if and only if we can write it in this quadratic form here for some positive semidefinite matrix Q. So this, again, this notation here means that our matrix Q is positive semidefinite. And if we can find a positive semidefinite matrix Q such that we can write our polynomial in this form, if such a gram matrix exists, then that certifies that a polynomial is a sum of squares. And just to reiterate, what I mean by sum of squares, SOS in this case, is it's a sum of polynomials squared. This X bracket notation here is a vector of monomials of degree D. So again, we started with a polynomial of degree 2D, and then the monomial vector will have all monomials of degree D. So what does this, again, what does this fact tell us? Well, we're searching over the cone of positive semidefinite matrices such that the coefficients of P equal certain sums of the entries, unknown entries of Q. So that's exactly a semidefinite program, the feasible region of which is called the Gram Spectrahedra. Now, with symmetric polynomials, if we want to write a symmetric polynomial as a sum of squares, it turns out that there's actually a couple of reductions to the problem size that you can do to the SOS program or the semidefinite program because it's a symmetric polynomial. So I'll talk about that now. We're going to keep in mind an SN action on the space of degree D polynomials. So again, I started with a degree 2D polynomial, right? Our symmetric polynomial is a degree 2D, but that monomial vector has all degree D monomials in it. So we're interested in really SN acting on that space. That has a matrix representation. I'm going to call it D sigma, which induces an action on the space of symmetric matrices by conjugation. So with this new action on the space of symmetric matrices X, I'm going to restrict my semi-definite program to the fixed point subspace, so the subspace of all symmetric matrices which are fixed under this induced action. And it turns out that that is enough for an invariant semi-definite program. So if we optimize over the PSD cone restricted to the fixed point subspace, we will get an optimal, a solution with the same optimal value as if we had optimized over the entire PSD cone. That's what this theorem by Gutterman and Perlow says. In fact, more generally, I'm interested in symmetric polynomials in large part because of the symmetric polynomial inequalities I'll talk about at the end. But their theorem applies to all finite groups. So if we have some semi-definite program that is invariant under a finite group G, then we can restrict to the fixed point subspace induced by the matrix representation that you have. And that means that we can look at polynomials invariant under any finite group action. Right, but we are interested in symmetric polynomials today, and I'm going to, again, this is an example that we went over in the pre-seminar, so again, apologies for those of you who saw it, but I just want to briefly go over the different reductions here. So what we mean by restricting to the fixed point subspace, it means that we're going to be, in the symmetric polynomial case, it means that when we set up this equation from the SOS fact, we can, instead of looking at all positive semidefinite matrices, symmetric matrices, we can restrict to the ones that commute with the SN action of, in this case, degree 2 polynomials and 2 variables. And when that plays out, we get that Q11 and Q33 are equal, and Q12 and Q23 are equal. So we've reduced the problem size of writing this polynomial as a sum of squares from a 6 variable problem to a 4 variable problem. Then the next piece comes from looking at symmetry adapted bases. So we have this SN action on the space of degree D polynomials, which has a matrix representation. We can calculate the change of basis matrix T. That block diagonalizes our matrix representation. And it turns out that that block diagonalizes our Q as well. Moreover, each one of these Qi tildes is associated to an irreducible representation of Sn. Right, so our degree D, space of degree D polynomials and n variables decomposes into its irreps with certain multiplicity. And that will inform this structure. So each one of these Qi tildes is associated to one of the irreps that appears in that decomposition. Moreover, each Qi tilde is broken up into, is further broken up into blocks, but now these Qi's are all equal. So they're the copies of the same matrix Qi. In fact, the size of those Qi's is equal to the multiplicity of the associated irrep, and the number of copies is equal to the dimension. So for example, we'll see that the trivial representation, irreducible representation always appears, but it'll have one copy because it's dimension 1. And then the size of it will be equal to the multiplicity. So the number of copies of, I guess, the trivial irreducible representation will be the size of the matrix, Qi. On the other hand, for example, the standard irrep will always have n-1 copies in it because it'll always be dimension n-1. Yeah, so let me go over the example to see how this plays out, and then I'll ask for questions. Good, so we had this first reduction, right? We went from we went from a problem with 6 unknowns to 4 unknowns. So we do need to do that first step before we can block diagonalize the matrix. And then we calculate the change of basis matrix T and block diagonalize our Gram matrix. So here you'll see it's the 2x2 block, one copy of the 2x2 trivial block. And then here you have the alternating. And this is again because the trivial irreducible representation in the decomposition of the vector space spanned by these monomials, the multiplicity is 2, but there's only one copy because of course the trivial irrep is one-dimensional. And then the alternating is also one-dimensional. There's only one block because there's only one copy of it in the decomposition. Yeah, so I'll take a minute and see if there's any questions. Okay. Okay, so you may have noted that I didn't actually use any information about the polynomial here, except for the degree being 2 and the number of variables, right? That told me what sort of space for the monomials that I'm in. And so this matrix here is actually the cone that we will optimize over for all degree 4 polynomials in 2 variables, right? So once we know the degree and we know the number of variables, the structure of this will always be the same. And so that's kind of, we started looking at that and trying to understand a little bit more what this will be. And that's what we call the Symmetry Adapted PSD cone, right? So it's specifically the PSD cone first restricted to the fixed point subspace and then block diagonalized in this way. So we started asking questions about, well, what's the structure of it? The first question we answered was the dimension of the PSD, the Symmetry Adapted PSD cone, right? Which essentially is how many, what is the reduction in the number of variables? It turns out it depends on the multiplicity of the irreps that appear. So we get that the dimension is exactly this sum. So the sum over I of m lambda I plus 1 choose 2, where m lambda I is the multiplicity of the irrep associated to lambda I, or rather qi tilde, which is kind of the upper bound of what you would expect it to be, right? So maybe I'll go back to this. The size of these QIs here is the multiplicity. And since they're symmetric matrices, the most number of free parameters you could have in there is going to be m lambda I plus 1 choose 2. And then there are multiple copies of it, but they're all the same, right? So for each irrep, we get the number of free parameters is exactly the size of the matrix, sort of. Except that, again, it's symmetric. So that's why we get the m lambda I plus 1 choose 2. So it hits the upper bound. The next question we asked was about the extremal rays. And so maybe for a bit of context, for those of you who don't know, the cone of positive semi-definite matrices, so the PSD cone, if we take a matrix in it, a positive semi-definite matrix of rank 1, and then we take all positive scalings of it, that defines an extremal ray. And in fact, all extremal rays are defined in this way. So all of them are defined by rank 1 matrices. And so we asked, okay, well, can we do something similar for the symmetry adapted PSD cone? And it turns out we can do sort of a similar process. So what we're going to do is we're going to pick some qi tilde, and we're going to make the qi block in it rank 1. But then the qi tilde, since there are m lambda I copies of the qi, is going to have rank equal to the dimension of the associated irrep, right? Because there's that many copies. And then, so we have some dimension rank equal to the dimension block. Then the rest of the blocks will zero out, and all positive scalings of that defines an extremal ray. So the ranks of the extremal rays are equal to the dimensions of the irreps that appear. And they're exactly that. So they're in bijection. There are no other ways of getting extremal rays. So it's kind of neat. I mean, I think you get, depending on what group, again, this generalizes actually to other finite groups. So you get things where you have no rank 1 extremal matrices that define extremal rays. We have, in the paper, we have an example of the icosahedron, which decomposes into irreps of dimension 3, 4, and 5. And so those are those matrices define the extremal rays for that symmetry adapted PSD cone, which I think is kind of interesting and different. Yeah, so I'll go on to the symmetry adapted Gram Spectrahedra after this. But before I do, are there any questions about this?
Can I ask a question about this?
Yeah.
So if you want to find all extreme rays, do you vary over the QI? Is that what you do? This theorem?
Yes. Yeah. I mean, if you want to find all the extremal rays, you would need to find up to, I guess, scaling all rank 1 matrices of each QI.
I see. Okay.
So the Q's here mentioned in the theorem, are we like when we define the QIs for the Q, are we talking about like in the block diagonalization, or have we assumed that it's already diagonalized?
Yeah, what we're assuming here is that we've block diagonalized it already. So these QIs, okay. Yeah, they're referring to the blocks in that form, which is really just a change of basis, right?
Right. So does that mean you can use any QI, Isabelle, or do we have? Is there some restriction on the QIs?
Well, we do need it to be positive semidefinite.
Yeah.
Aside from that, not really.
No. Okay. So every extreme ray of the usual of some low-dimensional PSD cone will appear.
Yes.
Okay.
Yeah. Exactly. So we kind of get these PSD cones where of size equal to the multiplicity.
Yeah. Okay. Thank you.
Mm-hmm. Cool. Okay, so we have these cones that we get, these symmetry adapted PSD cones. But what we're interested in is sums of squares, right? So we're gonna have some polynomial. We're gonna ask, is it a sum of squares? And we get that by intersecting this symmetry adapted PSD cone with an affine subspace defined by the coefficients, right? So that's, when we do that, we get what's called the Symmetry Adapted Gram Spectrahedron. And just as a reminder, right, in the general case, for any polynomial, we have big PSD cone, and then the affine subspace defined by the coefficient. So we intersect that PSD cone with that affine subspace. That gives us the Gram Spectrahedron. In this case, we've taken the same affine subspace, but now we're intersecting it with a smaller cone, right? The Symmetry Adapted PSD cone, and that's what I'm calling the Symmetry Adapted Gram Spectrahedron. And so we were able to, find some or study these for particular cases, but we weren't able to quite get past that, because for each choice of D, or 2D rather, so each choice of the degree of your polynomial that you start with, a number of variables, you get a different symmetry adapted PSD cone. So we looked at particular cases, starting with symmetric quadratics. So now we're in the degree 2 case, and any number of variables n. The symmetry adapted PSD cone is actually a diagonal matrix, or represented by a diagonal matrix, which means if it's positive semi-definite, if and only if the diagonal entries are non-negative, and so we actually get a polyhedral cone, even. Interestingly, the way this works out is that for any polynomial that you give me, any symmetric quadratic that you give me, that will correspond to exactly 1 point on the plane. So either the symmetry adapted Gram spectrahedron is empty if it's outside of this cone, or it's a point inside of the cone, right? So every point corresponds to exactly 1 symmetric quadratic. Now, this extremal ray here corresponds to the n-1 copies of the standard block. So that won't change as n changes, but the trivial block, which is a 1 by 1 block here, that corresponds to this extreme ray here. And as n goes towards infinity, the line starts moving up towards what I believe is the Q11 axis. So what we found is that in the limit, the ratio of symmetric quadratics which are SOS to all symmetric quadratics is actually 1/8. So you can kind of see it pictorially here, which is kind of a neat result. And this sort of plays into some of the work that's been done recently on the asymptotic behavior of these polynomials. Yeah. And then I'm going to move up to symmetric ternary quartics. So n variables, degree 4 polynomials are gram matrices. In this case, are going to be 6 by 6. Here we have the symmetry adapted PSD cone. So we have 1 copy of the trivial and 2 copies of the standard IREP. The alternating doesn't appear in this case, and we have that they're both 2 by 2 matrices. And now if we pick a particular symmetric ternary quartic, so I have it here written in the monomial basis, and A, B, C, and D are fixed coefficients. I'm going to, this will give me, right, we go back to the SOS fact. I'm going to equate this to the quadratic form, equate coefficients, intersect that with my symmetry adapted PSD cone. And then that gives me my symmetry adapted gram spectrahedron, which is actually the intersection of these two spectrahedra. So this comes from the trivial block, and this comes from the standard. And this actually, since it's a two-dimensional object, we were able to just completely describe the symmetry adapted gram spectrahedra generically for symmetric ternary quartics. So it turns out that generically, for a positive symmetric ternary quartic, the symmetry adapted gram spectrahedra will be the intersection of this left component of a hyperbola and this parabola here. The hyperbola coming from the standard block and the parabola coming from the trivial block. Typically, for a symmetric ternary quartic, which is positive, the gram spectrahedra, so the larger object, has the 8 vertices of the gram spectrahedron. So these are the rank 3 matrices in the gram spectrahedra. It turns out only 2 of those survive when we intersect with that fixed point subspace. So the symmetry adapted gram spectrahedra has only 2 vertices of rank 3, which again, I'll remind you from the pre-seminar means that those correspond to SOS decompositions of exactly 3 squares. But we also know that along the parabola, we get rank 5 matrices, and along the, except for of course on the vertices, and along the hyperbola, we get rank 4 matrices. So we have sort of a complete description of the boundary, which gives you descriptions of what the SOS decomposition will look like. Right? So that was kind of nice. We were hoping for something similar for symmetric ternary sextics. So here is the symmetry adapted PSD cone. In this case, the alternating does start to appear. And here I won't make you count it. I mentioned earlier that when we do this reduction in problem size, the first step is to go from the number of unknowns in the symmetric matrix down to some smaller amount with the dimension. And this goes, I believe, if I remember correctly, from a problem of 55 unknowns to 13. Right, so we see actually that the larger the problem, we actually get quite a bit of a reduction in problem size by doing, by restricting to the fixed point subspace. And so we were interested in the symmetric ternary sextic case in describing what the boundary would look like. Obviously it's a 13-dimensional, the 13-dimensional object. So we can visualize it like in the ternary quartic case. But what we did is some computational experimental data. We tried to find random symmetric ternary sextics. And then of those, we calculated like 100. And of those, 12 happened to be sums of squares. So that those are the 12. Each one of these graphs represents one of those 12 symmetric ternary sextics, which are SOS. And then we ran 1,000 random cost functions on them to see what the ranks would be for random cost functions. And you'll see here, the majority is rank 6. So somehow in the normal fan of the symmetry adapted gram spectrahedra, the majority of it will be rank 6 matrices, but we do also always get rank 4 matrices, nothing lower than that, often up to rank 8, possibly up to rank 9. Of course, we were using SDP solvers, so the numeric solutions there was up to some error, but yeah. I think, for future work, it would be really interesting to try to get a better sense of what these boundary pieces really are, get some description of them in terms of the actual equations. But yeah, this was a first step towards that, maybe. Andy, I think I will, yeah, so let me stop here for a second and ask if there's any more questions.
So if you had a special ternary sextic, do you think you could completely describe it?
A particular ternary sextic.
These are generic ones, right?
Yeah. So, well, generic in that they were randomly generated, but yeah.
I mean, I guess I'm not asking, I'm just asking if we had a specific example, or do you know specific examples for which you could compute it?
I don't. I do think if we had a particular example, I don't know that we could necessarily describe the entire boundary, but we could probably describe the vertices at least. Yeah. But yeah,
these graphs are not necessarily telling you vertices, right? You're just optimizing in some direction and
exactly.
So it could be a non-vertex.
Yeah.
Okay.
Yeah, absolutely. It's not entirely clear that, for example, the rank 6 matrices are the vertices in this case.
Yeah, I'm just wondering if some specific example could be really nice as opposed to, I mean, anyway.
Yeah, off the top of my head, I'm not really sure. I think that would be worth exploring though.
Sure. Thanks.
Any other questions? Okay, so that's a bit about some of the work that we've done in understanding from a geometric perspective symmetric polynomials as sums of squares. We also use this machinery to do some work with symmetric polynomial inequalities. So actually the motivation for all of this came from symmetric polynomial inequalities. So let me give a bit of background on that first. So we're going to start with a symmetric polynomial G. And I call the term normalized symmetric polynomial, I denote that by capitalizing the letter that we use for the polynomial. So in this case, it would be capital G. And all we're doing is dividing by some normalizing factor. So we take our polynomial G of X and we evaluate it on the all ones vector and then divide by that. So as an example, here's the power sum symmetric polynomial with respect to partition 3(1) in 2 variables. If we evaluate this on the all ones vector, we're going to get 2 times 2, so 4. And so the term normalized symmetric polynomial capital P with respect to partition 3(1) is just the same thing multiplied by 1/4. And so this notation is what I will use for the sort of common symmetric polynomial bases. So for the monomial basis, I will use capital M lambda. Similarly, for the elementary power sum homogeneous and Schur polynomials. And this gives us what we call Muir-Head type inequalities. So I have it listed here as one big theorem, but these statements were actually proven by a variety of people over time. In particular, Cutler, Green, and Scandera proved many of them. Sra was able to prove one of their conjectures later on. But let me maybe state one of these. So we're going to assume that our partitions lambda and mu are of the same size. then it turns out that the term normalized monomial polynomial with respect to lambda is less than or equal to, again, capital M with respect to mu on the non-negative orthant. So this notation here specifically means that we're restricting to the non-negative orthant. So this inequality holds if and only if mu dominates lambda in the usual dominance ordering on partitions. And we actually had, so we have similar statements for, or there are similar statements for the elementary symmetric polynomials, power sum, and sure, where one direction was proven by Cutler, Green, and Scandera, and the other direction by Sra. And we have one direction, so Cutler, Green, and Scandera were able to prove one direction for the homogeneous case, right? So we have that h lambda is less than or equal to h mu on the non-negative orthant, only if mu dominates lambda. And they conjectured that the other direction was true as well. But luckily, Professor Green actually came to our combinatorics seminar at Berkeley and talked about these inequalities and said he doesn't think that the conjecture is true. So I thought, hey, why don't we use sums of squares and see if maybe we can disprove the conjecture. So how would we do that? What's the strategy here? Well, what we want is, of course, a pair mu and lambda of partitions that are incomparable in the dominance order, but this inequality would still hold. And in fact, we were able to find such a pair. So in particular, for the partitions of 8, 4, 4, and 5, 2, 1, the polynomial h44 minus h521 is non-negative on the non-negative orthant, even though 4, 4, and 5, 2, 1 are incomparable in dominance order. And we proved this using sums of squares. So a similar polynomial, so it's not exactly this polynomial, what we did is we took the polynomial h44 minus h521 and inserted squares in them, instead of dealing with the non-negative orthant condition. So if this polynomial is non-negative, that implies that this polynomial is non-negative. And in fact, this polynomial here in our proof is a sum of 41 squares. So that means it's non-negative, which gives us the inequality statement. So that's quite nice. Just to give you a taste, again, I mentioned that the number of squares corresponds to the rank, right? So we have a 45 by 45 matrix of rank 41. This is the first line of the Gram matrix that we found. You may notice that the denominator grows quite a bit, or really the numbers grow quite a bit, and that's largely because we had to do sort of a rounding process. We got a numerical solution from an SDP, from an SDP solver, which we then applied rational rounding to get this exact solution for the proof. So this is just the first row of our 45 by 45 matrix. It's a bit much, but yeah, it was also not the only solution or the only counterexample that we got. So let me explain a little bit what this pose set is. For every arrow, h lambda minus h mu, it may be a little hard to see, but these are partitions of 8, 9, and 10. So every arrow is points to, I believe, lambda, and then starts at mu, right? So every arrow is a difference, is an h lambda minus h mu that has an SOS certification. The black arrows are also dominance order. So interestingly, for these 3 partitions, at least in 3 variables, which is what we did, for these 3 partitions, every time that the dominance order held, which by Cutler, Green, and Scandera implied non-negativity, we also got SOSness. So we never got a case in these examples. We never found anything where positivity held, but not necessarily SOSness. We always got an SOS certification, so we always found some positive semidefinite matrix. Those are the black arrows. The blue arrows are also an SOS certificate, but between partitions that are incomparable in dominance order. So what that means is that every single blue arrow is a counterexample. In fact, here you can see 4, 4, and 5, 2, 1. So this is the counterexample that we found an exact decomposition for, or an exact counterexample. But if you trust that the SDP solved it accurately using numerical solvers, then every blue arrow is also actually a counterexample. We just didn't go through the rational rounding with them. Yeah, so we were hoping to see if, even though the conjecture doesn't hold, if there was maybe a different poset on partitions that did give you the homogeneous case. So maybe there was some if and only if statement for just a different poset rather than the dominance order, but we aren't really able to see anything from here. But if anybody in the audience can recognize a poset out of this, or some sort of a rule, then I would love to hear it. Yeah, and I think that is all I have for today. Thank you again so much, and I'm happy to take any questions.
Let's first thank Isabelle for such a nice talk. Any questions?
So what happens for 7, Isabelle? Do you know that the conjecture is true, 7, 6, and so on?
Yes, yeah, actually. So in the paper by Cutler, Green, and Scandera, they report that up to partitions of 7, they had actually proven that the conjecture was true, which, there aren't all that many pairs of incomparable partitions up to that point. So it's, there's not too many things to check, I guess. And 8 was the first place they thought maybe there would be a counterexample. And in fact, yeah, 8 was where we found ours.
So did you use your symmetry adapted gram spectrahedra, or did it come later?
Yeah, so you'll notice that I guess the first line didn't look of the gram matrix, right? It's not really block diagonalized. We used the first step of the reduction, right? So we were only optimizing over matrices that commute with the matrix representation, the appropriate matrix representation, but we didn't block diagonalize at the time. I do think that we could probably have done a little bit more. It's one of the reasons the partitions only go up to 10, because our computers stopped solving at 12 at partitions of 11. But I think if we block diagonalize it and utilize that machinery, we might even be able to go a little further along.
Probably. It's cool.
Can I ask, how much of the SN representation theory comes into the proof?
Really in the fact that you can, that the matrices commute with the matrix representation. So that's the key piece, that we're able to do this reduction because of representation theory to the problem size, and that's why we're even able to solve these SDPs in the first place. But that's really where it is. It's in making the problem more accessible to us.
Nice.
So do you think you can extend this to symmetric functions?
Yeah, so that's the question I'm hoping to answer actually in the spring, right, is what happens asymptotically.
Yeah.
And my guess is actually that asymptotically these blue arrows will start disappearing as the number of variables increases. And so I think I have a conjecture that this if and only if statement holds in the limit. But we haven't been able to prove that yet.
Any more questions? Then let's thank Isabelle once again.